So if I transform into a feature space, my x's go to z1, z2, up to zn. Okay, and my y's remain the same. Nothing happens to the y values. The x values totally changed. Okay, because that's what gets transformed. Okay, and in order to run this algorithm in my z space, I need to compute dot products, need to compute dot product. Okay, zn, let's say for example, zn transpose zm, if I have two data points, or zn transpose x, okay, z, if I have a data point and a test point. Okay, so I need to compute dot products. Now, typically I would transform into that space and just compute the dot product in the simple, usual, Euclidean dot product way. And the question we're going to ask is it possible to compute this dot product in my z space and therefore run this entire algorithm without actually going into the z space? Question. Is it possible to compute the dot product in the z space without physically transforming to the z space? If we can, okay, then we can run this algorithm, because all it needs are the dot products. If I replace this entire algorithm with z instead of x, okay, all I need are the dot products in my z space. Okay. So if I replace this entire algorithm with z's, then this is basically supposed to be zn transpose zn. This is supposed to be zn transpose z, and this is supposed to be zn transpose zs. So, and as it is illustrated here, okay, one way to compute that is to actually physically transform into the z space and compute these dot products. Another way to compute them is maybe, give me a function that takes as input xn and xm and somehow magically produces zn transpose zm. Give me a function that would take as input xn and x and somehow magically produces zn transpose z. Similar here. If you could give me this function that can take xn and xm and produce the dot product in my z space, I can run this entire algorithm completely in my x space. And now, that's the punchline. I'm going to show you how we can construct kernels that compute dot products in nonlinear feature transform spaces without actually going there. So they take as inputs the actual vectors in your original space and return the dot product in your nonlinear feature transform space. If I can do that, I can run this algorithm in pretending as if I'm in that space. And I even have the final classifier, pretending as if I'm in that space. But I never had to go to that space. Okay, so let's do a couple of examples to show you that I can indeed compute this dot product in my nonlinear transform space without actually visiting there by suitably constructing the kernel. We'll start with a simple example where the transform is polynomial, and then we'll do an example where the transform is to an infinite dimensional space where it's not possible to go to that space, but we can still construct the kernel that gives us the dot product in that space, which is then a miracle, because then we can run this algorithm in that infinite dimensional space using that dot product, that kernel. Okay.